Last week, I think we had finished up to the filtrations, but there is one thing I forget to talk about because I have checked uh, from the other files, another versions of the files. So this some of these slides are not there, but the versions that I gave it to you in the Microsoft Teams, you will find these slides. So what I missed last week is about the head loss. As I told you, anything get jams in the pike or in a waterway, it always cleared the head loss. The same thing if we put the media in the filter, and if we want this water passing through this media, that would be the head loss. And if the worry get a clock, more head loss you can observe. So the head loss can be easily observed by monitoring the water levels. So if it's increased, the water levels will increase accordingly. And talking about the factors influencing the head loss occurring in the filters, there are a number of factors. For example, the depth of the filter, the depth of actually the depth of the media. So this is the depth. For example, in this figures, it was 300 millimeters. So if we expand it to 500 millimeters, the head loss will also increase. So this could be one of the major factor. The bed porosities. If you think about the pie, the bed porosity is more or less the same as the opening areas or the cross-sectional areas. The bigger porosities or the larger cross-sectional areas will minimize the effects of loss. But if the bed porosity is small, the loss will also high. Filtrations velocities filtrations velocities is equivalent to the flow rates divided by the surface areas of the filter bed. So this you will get the filtration velocities. This is also one of the prime factors resulting in the increase of the head loss. Other
อาจารย์ครับ
parameters like
อาจารย์แชร์สกรีนหรือยังครับ
our share screen เดี๋ยวแป๊บหนึ่ง sometimes I forgot to share the screen and sometimes I forgot to make a recording. Okay, but now I think everything is done. Recording the video and also the screens, the slides on the screens. Okay, so the other two parameters like viscosities and the mass density, these two are the physical properties of the fluids. If our fluids is just a water, these two parameters cannot be changed. Anyway, it is depending on the temperatures. So if the temperatures vary, these two parameters may be slightly changed. So these are the three major factors. And in order to determine the head loss, there are various equations you can use, but the simplest one, I think it's the first one. The first one is the common cosine equations. The loss is equal to the friction factor divided by the Chef factors, and you have to consider the porosities, and then the length of the media, the D in case of the pi, it is in diameters, but in case of the filter, it's not the diameters. You have to look for the definitions here. D is the grain sized diameters. D is the grain sized diameters in this case. But anyway, okay, another factors is the velocities. These velocities is not Vs is not the settling velocities, but Vs is the superficial filtration velocities defined as meters per second. So the definitions of terms you have to follow this bibliography, but the abbreviation uses here may be the same as the we have used it in the previous part of these chapters. For the head loss determination, you have to look for the definition in this slide. Okay, for this one, the first equation seems to be the simplest forms of the head loss determinations equations. It actually modified from the equations that we are all familiar. The loss is equal to F out over d v squared divided by 2g. Actually, this equation is the Darcy's equations. So from the Darcy's equation, so these two persons, he had revised these equations and becomes this one, and named these equations as the common cosinus. So this is probably the simplest forms of the head loss determinations equations. Other equations also can be used. Sometimes the engineers, they have conduct the experiments and they find better coefficients or better relationships developed during the experiment. So they have put that factors into the equations and then becomes another or the new one. We have several lost computations equations. Other equation that we also use it very often is the loss equation. Loss equations, the loss is actually the functions of the shape factors. This one is the shape factor, so it depends on the types of the grain. So if it's round and smooth, the shape factors will be one values. So if it's a kind of a clutch materials like the anthracite or the core, the loss generated due to this kind of factors are totally different than this one. That is why they put the shape factors here. And then we need the drag coefficient here. Discharge coefficients, the discharge coefficients. And then we need the porosities here. So you have to look at the definitions. CD is the drag coefficient, sorry, not the discharge coefficient. So sometimes I also confusing, but anyway, every time while using, we have to check the definitions again, and not just the definitions, we have to check the unit whenever you want to apply these equations. Okay, so there are a number of equations you can use. It depends on the parameters you have it in hand. Sometimes you want to determine just the coefficient of drags, but you don't want to go for the friction factors. You can use the Roche equations. Sometimes you have the informations about the filtration constants, for example, and kinematic viscosities, you can apply the other equation like a Fair and Hatch equations. Harssen's equation you can also use. So there are many equations, and some of these equations, most of these equations are the empirical formulas. As I told you, whenever use this equation, you have to follow the definitions and then check for the unit. Friction factors is the same as we determine in the by using the Moody's diagrams. You can find out the friction factors, but before obtaining these friction factors, you have to calculate the Reynolds number, and the Reynolds number, it's also important if you want to calculate the coefficients of drag or the CD uses in the Rost equations. The coefficients of drag is only used in the Rost equations, but not required in other equations. Okay, so now let's have a look at the example. So how do we determine the loss, especially the initial loss? In this equation, if you go through the questions, you'll find these filters will basically have the two types of the media. The first one is the anthracite, and the second one is the sand. We have in this question, they proposed two types of the filter media. The first one is the anthracite, and the second one is the sand. For the anthracite and the sand, so again, if I ask you which one should be put it at the tops and which one should be put it in the bottoms. So actually, the anthracite should be topped on the sands because the densities, the anthracite, the densities is much lighter than the sands. If you put the anthracite below the sands, and then when you do the backwash, the anthracite will be turning to the top layers again. So it doesn't matter. So anyway, we have to put the filter media. Sometimes we have to concerns about their physical properties. Anyway, for the anthracite, the thickness of this layer is 12 inches, and then the average size it's about 1.6 millimeters. It's an average size, okay, not the effective size. This one we use the average size. And then for the sands, the thickness of this layer is also 12 inches. And the average size is 0.5 millimeters. This filter is operated under the filtration rates of 160 liter per square meters per minute, or in a US customary units, about 4 gallons per square feet per minute. The temperature is 20 degrees Celsius. So under these temperatures, you have to look for the other physical properties of fluids. Depends on the equation you use. Sometimes you have to use the kinematic viscosities, and then or sometimes you may have to use the density. So this information you have to obtain it from the table under the temperatures of 20 degrees Celsius. And okay, so this example, they want you to use the Rost equations, shape factors, shape phi values. It's about the 0.75 and 0.782. Has anybody been to Greece? So if you had a chance to visit Greece, you'll find a lot of symbol like this. This is actually part of their alphabet. So everywhere there is a sigma, phi, epsilon, delta, gamma, and many others. And sometimes if you look at the Greek script, you will feel like this is a kind of mathematics, not really a language. Greece is actually located on the shores of the Mediterranean. It is one of very attractive destination, very fantastic. If you go there, you can enjoy the history, and you can also enjoy hopping at many islands in the Mediterranean. Okay, so this is the questions. Then how do we solve these questions? We are going to determine the initial loss by using Rolle's equation. So you have to look back at the how the Rolle's equation look like. So this one is the Rolle's equation. You need phi, you need the coefficients of drag, and you need the porosity, grain size, diameter, uh, uh, filtration rate, and of course the thickness of the filter layers. It is nothing but just try to substitute the values into the equations. Since the equation is this one, we need the coefficient of drag. We have to find out this one. So in order to get the coefficients of drag, you need the Reynolds number. In order to file the Reynolds number, we need the information about the filtration rates. So the filtration rate it's already given in the question. So just substitute everything into this equation. Then we'll get the Reynolds number for the anthracite layer, and do the same thing for the information obtained from the sand layer. Then we will get the Reynolds number about 1.1. And from this Reynolds number, again, we need to find out the coefficients of drag in the anthracite layer, and we need to find out the coefficients of drag in the sand layer. And finally, we obtain this number, 9.73 for the anthracite and 25.2 for the sand. And substitute everything into this equation. And finally, you will get the anthracite layer. The head loss due to this layer is about 0.26 feet. And the head loss due to the sand layers, it's about 1.91 feet. And the initial head loss is equivalent to the combinations of these two, since we have two types of the media, or we call it dual media. The initial loss is approximately 0.66 meters. If you compare with the typical criteria or the design's criteria, the initial head loss is in between 0.5 to 0.8 meters. so that the head loss that we obtain is within this range, so it's acceptable, not too high and also not too low. Too low, it's actually good, but it may be because of you provide a little bit thin depth of layers, which is actually not very good in terms of the solid removal efficiencies or the turbidity removal efficiencies. So these are about the head loss determinations. And of course, once it get clogged after being operated for some times, the head loss will increase because the porosities may not be approximately 0.4 or the same as when the media is clean. That is why after operation, for sometimes the head loss will increase. Okay, for filter backwashing, we have already talked about. For the dual media, we need the air auxiliary. Why is it like that? Just think about this one. Normally when we backwash, we have to apply the backwashing velocities slightly higher than the settling velocities, so it causes the abrasions. But if we have two types of the media, the sands, the settling velocities may be very high, but the anthracite, the settling velocities may be very low as compared to the sands. In this case, the backwashing rate should be with respect to the one which has the small settling velocities, or the backwashing velocities depends on the settling velocities of the anthracite, not the sands. So if we apply low backwashing rate, the sands layer, in this case, the sands layer will not be cleaned efficiently. So in this case, we may need to blow the air so that the air will help to increase mixings and abrasions so that all the dirt which get stick in the pore will be washed out. That is why this is probably the reasons why for a dual media we need the air auxiliary. So we need to blow the air together with the water. But if we only use the sands, just the single media, these types of the single media maybe during the backwashing, maybe the air is not required. So this is the photographs showing the water after backwashing. So it comes from the bottoms to the top. All the dirt are washed out. It becomes like the water in the rivers during the wet seasons, where there's a lot of suspended solids traveling along with. Okay, so these are about the these are all about the filtration process. Now we move to the next unit operation, which is the flotation. Flotations, just look at the spelling, Flotation, not FLOA. Okay, this one is correct. Flotations. This one is correct. So what is the objectives of the flotations? Flotations is also the unit operation used to remove the suspended solids, but we particularly used for the suspended solids which has the density slightly the same as water. If the density is slightly the same as water, the density of water is approximately 1, but for the sands, the density we all know that it's a 2.65. The specific gravity, not the density. The specific gravity is 2.65 for the sands, but there are some kind of suspended solids which has the density approximately same as water. They are really light, like a pieces of paper, or they are a fiber, or many other types of the suspended solids which are really light. Instead of we are waiting them to settle to the bottoms due to the gravitational attraction. If we do that, it may take long times, or the efficiency of removal may not be very good, as if there is a turbulence, there is a chance that the accumulated or the settled suspended solids will resuspend again. So in order we do the conventional way, we do in the other way. So we provide some kind of air bubble, verify air bubble. So this air bubble will get attached onto the surface of the suspended solids, that light suspended solids. So they can actually make them even lighter. The density is even lower, so that sometimes the overall densities of the suspended solids in combination with the bubble is smaller than water. So when it gets the density is smaller than water, it can actually move up to the surface, so that we can remove these suspended solids from the surface directly. We don't have to wait them settle to the bottoms of the chamber and collect from the bottoms. We don't have to do it in that way. That is the suspended sedimentation tank. But this one is we are trying to bring all the suspended solids from the bottoms to the tops, and we remove it from the surface. So we only apply this process for the particles with the very small settling velocities. We can use this technique to remove the algae in water. As you know that the algae, the densities of the cells itself is very small. So flotation would be a good idea to apply it when we want to separate the algae from water. So this is about the objectives and the principles of the flotation. There are essentially three types of the flotations. The first one is the dispersed air flotation. Second one is the vacuum flotation, and the last one is the dissolved air flotations. So there are essentially three types of the flotation we can use, but the most efficient one is the last one, the dissolved air flotations, or in short, sometimes we call it DAFT, DAF. DAF actually stands for D, A, and F. So how the first one look like, the dispersed air flotation. The dispersed air flotation is nothing. So you have to look at the pictures at the corner, lower, low, and left. These pictures. Basically, we provide the air bubble, as you can see it here. So we blow the verified air bubble. So we try to blow the bubble with the size as small as possible. But anyway, even just a small one, the bubble size still 0.1 to 1 millimeters diameters. 1 millimeters diameters bubble size is quite large as compared to the size of the suspended solids. So this might be a drawback of this process, because the dispersed air flotations, we cannot do anything with this. Whenever we blow the air, the size, it's when it try to move up, the bubble, one bubble may be combined with another bubble, it becomes even bigger. So when it come out from the air nozzle, uh, maybe the size could be a 0.1 to 1 millimeters, but when it move up, one bubble will combine with other bubbles become bigger. So when it gets bigger, it may not be very efficient to remove or to bring suspended solids from the bottoms to the tops. But anyway, this is a kind of concepts we can use, and some particular industry they also use this dispersed air flotations, especially the pulp and paper industry. Do you know the pulp and paper industry? Their raw material is a pulp, so they have to collect whatever the woods or the reused paper, and then they have to dismantle this material and make them becomes just something look like a pulp, and they only use that pulp to make a paper. So the pulp is actually very light. They are very light. They are big in terms of the size, but in terms of the weight, they are very light. So instead of we try to let them settle to the bottoms of the chamber, then we provide the air bubble, bring them to the surface. Then we remove all these floating objects by using the skimmer. The floating objects above on the surface generally we call scum, SCUM. All these scum will be removed where the facilities that we provide. So dispersed air flotations is just the flotation tank. We blow the air directly, blow the air with the very fine bubble. The size could be less than 1 millimeters. But anyway, this one is actually not very efficient. Sometimes it creates too much turbulence in the tanks. Even this tank is the flotation, but somehow they still need just the gentle turbulence. They don't need vigorous turbulence occur. But in a kind of the dispersed air flotations, so we just blow the air directly. So there's a possibility that the turbulence, strong turbulence will occur, and this strong turbulence will even try to break the bond between each floating objects. We use the skimmer to remove all this scum, and these floating materials will be collected in this chamber, and this chamber will later on be sent to the dewatering process or to the anaerobic digestion unit. The bubble size itself is the limitations of this process actually. That is why this process is not very popular for particularly used for some suspended solids removal. The details about these flotations, how it works, I think you can start it by yourself. And then the second type is the vacuum
อาจารย์ครับ
flotations ครับ
วันที่7นะครับ มันตรงกับวันอาจารย์ไฮดรอลิกนัดพรีเซนต์นะครับ แล้ววันที่7เราสอบพาร์ท first part ใช่ไหมครับ
ครับ
คือมันตรงกับวันที่เขาอาจารย์ไฮดรอลิกเขาให้พรีเซนต์นะครับ
แต่เขาพรีเซนต์ตอนเย็นเหรอ
ใช่ครับ
ตอนเย็นเหรอ
อาจารย์สอบกิจตอน 6-4 โมงครึ่งใช่ไหมครับ
ใช่ใช่
ไฮดรอลิกผมว่าพรีเซนต์ก็น่าจะช่วงบ่ายประมาณบ่ายครับซึ่งมันก็อาจจะยาวมาถึงตอนอาจารย์สอบเลยหรือเปล่าก็ไม่รู้
เหรอ เอาไง
คื
ดี
อถ้าเลื่อนเป็นช้ากว่านั้น สอบแลบก่อนวันที่13แล้วค่อยสอบเฟิร์สพาร์ทอีกทีหลังจากนั้นนะครับ
อะไรนะหมายถึงแลบกับ
เพราะก็แลบฟิกไปแล้วว่าวันที่13เพราะนั้น
ใช่
first part ก็เลื่อนไปหลังจากนั้นก็ได้ครับ
วันจันทร์ไหมล่ะ ถ้าอย่างนั้น
วันจันทร์
วันจันทร์เดี๋ยวนะผมดูปฏิทินก่อน7 8 9 10วันจันทร์วันหยุดวันจันทร์วันหยุด
หมายถึงวันจันทร์อาทิตย์เดียวกับวัน
หลังจากนั้นหลังจากวันที่7
อ๋อเดี๋ยวอันนี้เดี๋ยว
อาจ
ต้อง
จะเป็นวันอังคารไม่งั้นอาจจะเป็นวันอังคาร
อาจารย์คะวันอังคารพอดีว่ามีเรียนนะคะอาจารย์
เย็นนะตอนเย็น
มีเรียนตั้งแต่5 โมงถึง2 ทุ่มค่ะ
เหรอเอาวันไหนดีถ้าอย่างนั้นแลบมันวันที่13ใช่ไหมแลบนี่เราสอบในชั่วโมงนะไม่น่าจะมีปัญหาอะไรสมมุติว่างั้นสมมุติว่าวันศุกร์คือวันที่อะไรนะฮะวันศุกร์ถัดไปเนี่ย14ถูกไหม
วันที่ใช่ค่ะวันที่
14เอาเป็นครั้งที่1แล้วครั้งที่2จะเป็นวันไหนอะครั้งที่2
ครั้งที่
เอาหลังจาก
จะ
นั้น
เป็นวันที่20แต่ก็จะเริ่มสอบแล้ว
เอาก่อนสอบไฟนอลจะดีกว่าวันไหนดี14แล้วก็เป็น17ไหมล่ะวันจันทร์ ตอนเย็น
คือตอนเย็นวันจันทร์พวกหนูก็มีเรียนนะคะถ้าวันจันทร์เป็นกลางวันได้ไหมคะ
ได้ฮะได้
น่าจะลองถามเพื่อนๆดู
17บ่าย
เผื่อเขาติดเรียนด้วย
จันทร์บ่ายเป็นยังไงถ้าจันทร์บ่าย
จันทร์บ่ายหนูมีติดเรียนแลบไฮดรอลิกอะค่ะ
ฮะจันทร์บ่ายเนี่ยนะ
ใช่ค่ะแต่ว่ารุ่นปี61ไม่ได้เรียนแต่ว่า60ยังมีเรียนอยู่อะค่ะ
อ๋อเหรออังคารเมื่อกี้ก็ติดใช่ไหมอังคารเย็น18 21เนี่ยผมไม่อยากจะนัดเพราะว่าเดี๋ยวมันจะไปกลัวผมกลัวว่ามันจะไปทับกับของอันอื่นเขาหรือเปล่าหรือเราจะเอา21เย็นวันศุกร์21วันศุกร์นี่มีใครว่างวันไหนว่างกี่โมงบ้างฮะวันศุกร์21ไม่งั้นอาจจะชิฟไปอีกอาทิตย์หนึ่งครั้งที่2นะตอนนี้ครั้งที่1นี่14ใช่ไหม
ได้ครับได้ผมไม่มีปัญหาครับแต่
21นะ
คือเอาครั้งที่2
14นะตกลง14นี่โอเคนะ14 13 14นี่โอเค13 14ไม่มีปัญหาแล้วก็อีกครั้งหนึ่งอีกครั้งหนึ่งเอาเมื่อไหร่ดี20นี่มันก็เริ่มสอบแล้วใช่ไหมในชั่วโมงของเราตอนเช้าไหมล่ะ20ในชั่วโมงของเราตอนเช้าแต่ว่ามันเป็นวันสอบแล้วอะพฤหัสเช้าไปเลยเวลาปกติ9:30มีติดสอบไหมฮะ
วันที่21
เขายังไม่ได้ประกาศสอบอะค่ะอาจารย์
อ๋อเหรอ
ใช่ค่ะ
ถ้ายังไม่ประกาศก็ต้องอาจจะต้องนัดตอนเย็นไว้ก่อนจะดีกว่านะ19เย็นพุธ19เย็นไหมเอาอย่างนี้อยากได้เย็นวันไหนอะพุธพฤหัสศุกร์อย่าเลยถ้าเป็นตอนเย็นอยากได้เย็นวันไหน19กับ20 แต่ว่าครั้งที่2นี่เราสอบไม่เยอะนะครั้งที่2เราสอบแค่ชั่วโมงครึ่งเอง
คือถ้าเป็นตารางของผมอ่ะมันจะมีว่างแค่อันนี้ผมรู้สึกว่าที่ว่างตรงกันก็มีแค่วันศุกร์ครับเพราะวันจันทร์รุ่นพี่เขามีเรียนตอนบ่าย วันอังคารรุ่นผมรุ่นผมก็จะมีบางคนที่จะต้องเรียนตอนบ่ายก่อนตอนเย็นวันพุธก็ทำแบบ
งั้นศุกร์เย็นสรุปแล้ว21เย็นศุกร์เย็นน่าจะว่างหมดใช่ไหมศุกร์เย็น
ใช่ครับถ้าเกิดไม่มีอาจารย์คนไหนมานัดวันศุกร์นะครับถ้าเกิดเขามานัด
ไม่งั้นเรานัดไปเลยดีกว่าเขาจะได้ไม่มานัดทับกันนะถ้างั้นเอา14กับ21แล้วกันงั้นก็ช้าไปอาทิตย์หนึ่งงั้นจากเดิม7กับ14เปลี่ยนเป็น14กับ21นะถ้าอย่างนั้นโอเคทีนี้กลับมาที่เรื่องflotations okay, so for the dispersed air flotations, it's nothing complicated. We just blow the air in the flotation tank. But the second one is the vacuum flotations. The vacuum flotations is like we provide the completely closed tank. Okay, at first we provide the air into the wastewater or the waste containing suspended solids. We provide the air so that suppose this is the suspended particle. So if we provide the air bubbles, so air bubbles we get attached on this once we blow the air bubbles into this water body. So the entire densities will be lighter. That is why it can actually move up to the surface and become scum. That is why we can use the skimmer to remove. So for the vacuum flotations, we put the wastewater. ฮะสกรีนอีกละลืมนะฮะokay, so in here we apply the air bubbles and then this air bubble can actually get attached to the suspended particles. It actually make the overall density even lighter, so that it's easy to move up to the surface and becomes a scum. That is why we can use the skimmer to remove them and push them into the trash collector. For the vacuum flotation, we actually put the wastewater into the chambers, and we also provide the air until it gets saturated. So it's saturated with the air, and then after saturate the wastewater with the air, we closed this tank tightly. We closed this tank tightly, and then we apply suction. We apply the suctions, applying the vacuum pumps in the in this container. So what will happen if we apply the suctions? The air which completely dissolved and remained in the wastewater under the saturated conditions will again re-bubbles. In fact, they completely dissolve, but once we apply the suctions, the bubbles, the air which completely dissolved will again become the bubbles. And as it becomes the bubble, it's also the same thing happened in the dispersed air flotations. So this bubble formed due to the suctions will get attached on these solid particles and bring these solid particles to the surface. So this is a kind of we apply the vacuum pumps to create the negative pressures inside these containers. But anyway, this has to be a tight container. That is why we can convert the air, which is completely dissolved, to rebubbles again. And this bubble will bring all the suspended solids to the top, to the surface. So this is how the vacuum flotation work, but this one is actually not really practical because we need to apply the vacuums. So anything related to the use of the vacuum is actually not suitable for the application with the largest capacities. We need a lot of capacities to withdraw the air. So vacuum pumps is only suitable for the small capacities productions only. That is why this kind of system may not be very popular. Then the last one is the dissolved air flotations. In short, we call it DAF. Dissolved air flotations. For this, dissolved air flotation is something different from the other two. These two diagrams shows how the DAF work. You may look at this one, the right one. This one is the mixing tank, where sometimes we add the chemicals, flotation aids. Flotation aids, mostly they are the polymers. They have capacities to hold the suspended solids together. They are not the same as the coagulants or the flocculants, but they are just a kind of some kind of polymers that we used. But anyway, it depends on the suspended solids characteristic. But if the suspended solids characteristic has a kind of the charge around the surface, so in that case, the flotation aids could be chemicals with the charge. But anyway, this one, the influence is faded into the mixing chamber where the flotation aids are added, and then these liquids will be pumped to this flotation tank. This one is the main tank, the flotation tank. In this tank, we do not provide any aeration facility. So it's just the retention tank, it's just the conventional tanks where the surface equipped with the skimmer. So the flotation process actually takes place in this tank. But how it works, because we did not install any the flotation facilities. They do it like this. Part of the effluents from this tank, part of the effluents from this tank will be returned and put it into the retention tank. This retention tank is very small, not a large tank, but within this tank, what they do, they actually saturate the liquids, with the air. But the air that they blow it into the water in this tank, they blow it under the pressures 2 to 4 atms, atmospheric pressure, not under the atmospheric pressure like a case of the vacuum flotations or the dispersed air flotations. So they blow the air under the pressures 2 to 4 atm. So under such a high pressures, more capacities of the water can actually absorb the air. Like in case of the oxygens, under the normal conditions, saturated dissolved concentration would be 7 to 8 milligrams per liters, but sometimes it can actually goes up to 14 or 15. That conditions we actually call the supersaturated conditions. This one is also the same, but in order to make the solubilities under the supersaturated conditions, so we need much higher pressure, not under the normal pressure. So we apply a 2 to 4 ATMs within these retention tanks. This tank must be tightly closed and properly equipped with the pressure gauge so that we can actually observe how the pressure is going on inside this chamber. So once we supersaturate the liquids, actually it's the effluent, so it must be a kind of clean water, or the water with lower suspended solids. So we saturated these liquids until it reached the supersaturated conditions. And after that, we put it back again into this flotation tanks. So it's just like we make them supersaturated. But once we open or once we transfer the liquids in this tank and put it in the flotation tanks again, what will happen to the bubble? The bubble will reform again, but reform it under the pressures of 1 atm. So it's a supersaturated, but when we release the valve, the bubble, which already dissolved under the supersaturated conditions, if we change the pressures, if we reduce the pressure from 2 to 4 atm to just 1 atm, it gains over the saturation capacity. So in this case, the air bubbles will reforms again. So it will reform it in this flotation tank. That is why within this flotation tank, we don't have to equip the any aeration facilities, because all the air is blowing into the water inside this tank, and then only when it we released the water or we exposed the water to the atmospheric pressure, or the bubbles will form in these flotation tanks again. And again, once it formed the bubbles, all the bubbles can actually bring the scum to the surface, and then we can use the skimmer to remove this scum. So this is how the dissolved air flotation works. These are list of the basic components of the dissolved air flotations. The DAFT, or the dissolved air flotations, are one of the most common unit operation uses in the power in the wastewater treatments in the pulp and paper industry. Not just the water and wastewater treatments. Sometimes we can also use the flotations in the sludge thickening, which we will talk again in the last chapter. The sludge from the bottoms of the sedimentation tank, we need to handle them. We need to remove the water from the solids. So what we want is just the solids, so that we can put these solids or the sludge into the some kind of the containers with very low moisture, so that we can carry from the plants to the disposal sites. So we want the higher percentage of the solids in the sludge. The very first unit for the sludge treatment, it's we can use the thickener. We have to use the thickener. The thickeners, there are two types of the thickeners, gravity thickeners, and another one is the flotation thickener. So sometimes the flotation is used in the sludge treatment process. They can actually make up the concentrations of the sludge up to 10%. So this flotation thickening is actually very suitable for the handling the sludge collected from the wastewater treatment plant, especially the sludge generated from the activated sludge process. Activated sludge process is the name of the process typically used for the wastewater treatment. So we will talk about the activated sludge process in details in the next chapter. So they are all the organic sludge. So putting all the organic sludge together, and if we use the gravity thickener, no air is provided, it is possible the organic sludge accumulated in the gravity thickener may generate some kind of unpleasant smell. But if we use the flotation, it is much better because oxygen is provided, so we can actually minimize the effects of the unpleasant smell, which may disturb the communities nearby. Okay, so these are the applications of the flotation unit we can actually use in water and wastewater treatments, and we can also use in the sludge treatments. And these are the operational parameters. The flotation process efficiencies of the flotation process depends on the composition, natures of the particles, and it also depends on the amounts of air is supplying. And sometimes we need to add some kind of the chemicals to promote the flotation process. Okay, so that is all about the flotations. Then the next unit operation actually should be a unit process. It's an adsorption. Spelling is A-D, adsorption. This one is correct, not A-B. You may be familiar with A-B, but this one is A-D. Okay, adsorption. Adsorption is actually the process where we used some kind of material, and then the pollutants or the contaminants can actually get attached onto the surface of that kind of material. So that these adsorptions, it's actually aimed to collect or remove the fine particles or even a soluble substance that can actually exist in water. So we try to remove all these contaminants by using some kind of we normally call the adsorbent. So one of the most common adsorbent uses in this process, you may already know, it is the activated carbon. I'm not sure whether you have ever heard about this activated carbon. Activated carbon is actually one of the adsorbents, one of the very common adsorbents used in the water purifications. In your house, some of your house, I think you have a kind of filtered machines, and inside there is a filter cartridge. So inside that filter cartridge, they are mostly put the activated carbon, not any other forms of the filter media. We recognize them as the water filter machines, but actually inside they put the activated carbon to carry out the adsorption process and not the filtration process. So they are mostly function the adsorption, not the filtration. What is the major proposed? What is the major target pollutants that we need to apply in this process? The major target pollutants to be removed by this process is basically the contaminants or the substance which could cause unpleasant taste and odor. So the contaminants which cause the unpleasant taste and odors is actually good to be removed by using adsorbent like the activated carbon and many other types, zeolite, clay, and so on. So this could be an adsorbent. These adsorptions. Okay, adsorbent most commonly used is the activated carbon, as I told you. Sometimes we can use the zeolite. They are the inorganic adsorbents, silica gel, clay. This could also be used, and sometimes we also use this one instead of the activated carbons. But zeolite, it's actually more expensive as compared to the activated carbon. Activated carbon is actually good enough to remove things like compounds associated with the taste and odor generation, and also they can remove some trace pollutants like the remaining organic compound. In some country, they require the COD in the wastewater even less than 60 milligrams per liter. In Thailand and many other countries, we prefer to have COD smaller than 120. But in some country or in some area, in some cases, they want the COD to be less than 60 only. In a very sensitive areas, they want the COD it's even less than 60. Comparing to the BOD, normally BOD required to be less than 20, but in some sensitive areas, some authorities they want the BOD to be less than 10, like that. So in order to make a very good effluent quality, there is no other way. Biological process and typical coagulation, circulation process, filtration, sedimentations and filtration processes. These conventional processes can actually cannot actually remove these trace pollutants. So we have to apply some kind of advanced treatment process like this one. Adsorption to further remove the remaining the organic compounds. Only this process and some other advanced process can actually reduce the COD contents to be less than 60 or even 50 milligrams per liter. So that is why we normally consider this process as a tertiary treatment, not the primary or the secondary treatment. Adsorption sometimes also refers to the actually it's different. The ion exchange is totally different from the adsorption, but it's also part of the process used to remove fine particles or the trace pollutants. Ion exchange only function with the removal of the contaminants of the pollutants with the a charge or with some specific a characteristic depending on the types of resins used. Okay, so we will talk about this again later. These are the list of the pollutants that can be removed. The remaining detergent, the dye, whatever the process that doesn't work with the color remover, you may have to think about the adsorptions. Other process may not be efficiently remove the colors, especially a true color. Some correlated solvents like pesticides, conventional process may not be able to remove, but adsorption can actually completely remove this one. Phenolic compounds, taste and odor producing compounds, micropollutants, or any pollutants that actually exist in nanograms or in micrograms. Normally, when we talk about the coagulations and flocculation, we always talk about in terms of the milligrams. It can actually remove the milligrams of the contaminants very well, but coagulations and floculations cannot remove a pollutants in terms of the nanograms or the micrograms. So only this process can actually possible. Heavy metals also can be removed by using both the adsorptions and the ion exchange. Mostly we apply the adsorption in the both a water and wastewater treatment system. Actually, for a wastewater treatment plants, sometimes we also used we also apply some process to remove nitrogen and phosphorus. Conventional process cannot remove nitrogen and phosphorus, but if we provide or if we equip some extra unit process or unit operation, we can remove these nutrients compounds. The removal of the nitrogen and phosphorus are also part of the tertiary treatments or the advanced water and wastewater treatment process. As I told you, we normally use this process to remove a micro pollutants. If we want to, for example, reuse that treated water, we may apply this process. For example, if you want to actually water supply source, it could be any types of water, not just the surface water or groundwater. Wastewater can also be a water supply source. The waste coming from the household, black water, gray water, a combination of these two, black water and gray water, becomes a domestic wastewater, as we all know that. This domestic wastewater can also be used as the water supplying sources by the technologies. They can actually the technologies can actually completely remove all the contaminants from the wastewater. But the only things right now we are not using the domestic wastewater as the water supplying sources. It's mainly because the aesthetics problems people do not accept. But by the technologies, everything is possible. Even wastewater, we can actually turn them into a drinking water. But just a matter of the aesthetic, the public acceptance, maybe mostly the people they don't want to drink or use the water from the producers from the domestic wastewater like that. So if you want to reuse, or if you want you want to produce the drinking water, very good quality water from highly contaminated water like the domestic wastewater or the industrial wastewater, the last process could be adsorption, the very last process before applying the disinfectants. Adsorption could be the last one. We also use the adsorption for the tertiary treatments, removal of the remaining COD, as I already mentioned. One of the most common adsorbent used in the adsorption process is the activated carbon. There are essentially two forms of the activated carbon. One is the granular activated carbon. In short, we call it GAC. And then another forms of the activated carbon is the powder, not the power. D is missing. A powder activated carbon, just like a powder, very fine particles. Physical characteristic is like they actually look like a very fine particles, like a towel that you apply to your body after taking a shower. Okay, so there are two types of the activated carbon. The one with the granular forms, we mostly used as a fixed column, just like a filter. Instead of putting the sands or anthracites or the cover, so we put the activated carbon, granular activated carbons instead. But for the powder we use it like this. Sometimes we use the tank, and then we provide a mixing, and we put the wastewater inside this tank. And if we want to apply the adsorption process, so in here we may add the powder activated carbon, because the powder activated carbon, the particle size is very small. They can actually spread all over this water body. So the efficiencies of removal, efficiencies of the adsorption is very high. As the surface area is very large, the smaller particles will be, the larger surface areas. If you compare it in 1 units of volumes. But a powder activated carbon is not suitable if you want to put it into the column like this. As the size is very small, if we use it like this, within few hours, you will experience the clogging problems or the higher heat loss immediately generated. So we use the granular. The granular one is like the grains of the sands or the gravel. It depends on the size. It depends on the types that it depends on the purposes of using. So size ranking from a smaller to the larger one. The flow directions could be a downflow, or the this one is the downflow, or it could be like this. So we put the granular activated carbon inside, and then we also can use the upflow. Actually, if I asked you which one is better, downflow or the upflow, which one is better in the case of the adsorption? Downflow or the upflow? But for the filter, we prefer them to move downward, because we can make use of the gravitational force to bring all the water passing through this media. For the filter, we prefer to use the downflow, but for the activated carbons, we prefer to use the upflows. because the upflows always created the flooding conditions inside this media. So water inside the pores inside this adsorbents will be always flooded with water, and this will enhance the efficiencies of removal. But if you use a kind of downflow, so the particle just sometimes just move out or escaping from the adsorbents layer, so that the upflow is actually better. But in terms of the operations, upflow it's actually more complicated in terms of the operations. You need like pumps to push the waters from the upwards to from the bottoms to the tops. But for the downflow, maybe the pumps is not required, or we don't have to use the pumps all the times if it's downflows. But if it's upflows, we need the powers. We need the pumps all the times. Solute removal occur at the rather narrow top zones. The adsorption normally occurred like this. Suppose this is the column, and here we put the granular activated carbons here. Then if we put like the upfold directions, at the beginning, the solutes or the contaminants will actually adsorbed on the top zones or the top layer. So tops means the very first zones that exposed or get in touch with the water. So if we fit the waters from the bottoms to the tops, here will be the zones where the solutes or the adsorbents get adsorbed in the adsorbent. And once it's full, the lower layers or the next layers will function. Okay, so accumulations of the solids will only occur on the layer where they actually exposed to the water. But in the upper layer or in the next layer, it will only function when the adsorption capacities of the top layer it's completely full. Okay, if it's not fully adsorbed, so the lower layer will never will not functions again. So once it full, then the next layer will be used to adsorb these pollutants. And once it full again, so next layer will adsorb like this until it reach the last layer. So if it reached the last layer, this adsorbent will not be efficiently remove the contaminants. So in this case, what we need to do, we need to replace these adsorbents, or we have to bring them to what we normally call the regeneration. Okay, so this one is the photographs of the activated carbon. Activated carbon is totally different from the charcoal. Charcoal, they are also 100% carbon, but they may not have like a surface area, very high, very large surface area like the activated carbon. Activated carbon is actually very porous, and then in terms of the surface area with respect to the volumes, it's very large. So they have lots of the capacities to absorb the pollutants or the contaminants. So this is a kind of the things that makes the activated carbons totally different from the charcoal. Okay, in terms of the surface area. Okay, for the charcoal, the surface area may not be large as compared to the activated carbon. There is an indicator which say whether this one is the activated carbon or not. There is an indicator. There are several parameters we can measure whether this carbon is the activated carbons or just the normal carbons or the normal charcoal. Okay, but anyway, the granular activated carbons actually it looks like this, like a grain. In fact, I'm not sure about this photo because if it's the activated carbons, it actually completely black like this, not the brown one like this. I'm not sure. Maybe this one is a kind of a coffee, maybe not the carbon. It turned brown, or I don't know. Maybe after regenerations, I'm not sure about this one. But anyway, activated carbon, it's totally black. After used for some times, we have to do the regeneration. Carbon, you don't have to dispose it, but you may not have a kind of equipment to regenerate them. That is why you have to dispose and then buy the new one. But in fact, the activated carbon we can actually regenerate. Regenerate, what does it mean? It means that we bring these carbons or the adsorbents which are fully adsorbed, and then we take it out and we remove all the adsorbate. The activated carbon normally we call the adsorbent. And then the pollutants we normally call the adsorbate, BATE. Activated carbon normally we recognize as the adsorbent, but for the pollutants we recognize as the adsorbate. So regeneration is a kind of process where we try to remove the adsorbate from the adsorbent. We can use the stream or apply the heat, put all the adsorbed carbons into the vessel, providing the heat. So all the pollutants will be burned and or maybe vaporized. So it's all gone after regeneration. Sometimes we have to use the chemicals to regenerate. It depends on the adsorbents, and it also depends on the types of the adsorbent. So once we regenerate it, after regenerations, all the adsorbents can be reused again. For the adsorption, we can apply the continuous flow system, or we can apply the batch flow system. So what are the difference among these two? The batch flow system, as I told you many times, we have a vessel. We put everything into the vessels or the containers. All the reactants, we put it in the containers or into the vessels. Then we close it. Let it be for like a, it depends on the reactions. It could be a few hours or maybe several days. Do you know the fish sauce? Fish sauce manufacturing process. They bring the fresh fish and then they put the sauce and the fresh fish. I don't know what kind of fish they commonly used, but fish and then salt. They put it into the containers and let it be for like 1 year. All the fish meat will be dissolved, and then the taste will get into the fish sauces itself. so that we take the liquids from these vessels or from these containers and filter and properly try to purify it from the possible contaminations, and then put it everything into the bottles and sell. So the fermentations of the fish sourced, it's also coming from the batch flow system. Continuous flow system. I think everyone are familiar with the continuous flow. The continuous flow, it's like always there is the inflow and the outflow, and the times that the liquids staying inside the chamber, we can actually determine it by taking volumes divided by the flow rate. So this is the characteristic of the continuous flow system. Here are the list of the list of the factors factors influencing the absorption. Agitation, or characteristic of the adsorbent, the solubilities of the adsorbent. So these are the major factors affecting the performance of the adsorption, not only just for the activated carbon, but also for the other types of the adsorbent. pH, temperature. So these two are the prime factors affecting almost every chemicals and biological reactions. The higher temperatures generally poses the higher reaction rates, degradation rates, whatever, but it's associated with the reaction rate. pH, the lower pH will cause the acidic conditions, and the acidic conditions may actually affect the absorptive capacities. So basically, these are the major factors affecting the absorption process. Okay, I think that is all about the two unit operation, absorptions and flotations. Flotations is not flotation is still the secondary treatments, but for the absorption, we normally consider this absorption as the tertiary treatments or the advanced water and wastewater treatment process. We consider them as part of these processes. Now we move to the last sections of this chapter. This one is the last because the disinfections we have already talked about it last week. Softening is a process where we use to remove the hardness. There are 2 or 3 types of the hardness removal process, but softening is one of the most commonly used. We can use like a resins to remove the hardness, because we know that the hardness is originated from the dissolved of the polyvalent cation, especially calcium and magnesium. So if we could remove the calcium and magnesium, we can say that the hardness it's also removed accordingly, because the hardness is originated from the presence of the polyvalent cation. The hardness. What are the problems associated with the hardness in water? The hardness may cause the scums in the bathtubs, in a faucet, in a bathroom toilet, and so on. And it will leave the white, hard, and crusty deposits on the scale on these toilet facilities or in the bathroom facilities. That is why sometimes the hardness is an unwanted contaminants in water. Hardness is actually divided as the sum of the polyvalent cation. We can compare all the polyvalent cation, but if we want to compare, of course, we need to make them in the same unit or in a consistent unit. The unit is normally expressed as the milligrams per liter as calcium carbonate or milligrams milliequivalents per liter. So, but anyway, we prefer to classify them in terms of the milligrams per liters as calcium carbonate. We discussed this slides once during we do the experiments on the hardness. The hardness rank from the 75 to 100 milligrams per liter as calcium carbonate. This one is actually moderately hard. We prefer water with moderately hard characteristic. We don't want too soft water or too hard water. That is why the hardness is the only parameters. We are not aiming to remove it 100% because the removal of the hardness 100% is not possible. Okay, so the hardness should be in a moderately hard range, ranking from 75 to about 100 milligrams per liter as calcium carbonate. Yeah, sometimes it goes up to 150. 150 it's still acceptable. 120 it's common. But in terms of the cation, the predominant contributors are the calciums and magnesiums. There was one question I asked during the midterm exams. For what reasons? Why we need to know how much of the hardness is caused by calciums and how much of the hardness is caused by the magnesiums? Why we have to know? The answer is the calcium hardness and magnesium hardness. They are both, although they are both the hardness, but in terms of the removal, magnesium hardness is much more difficult to be removed as compared to the calcium hardness. So if we know this amount, we can actually propose the amounts of the chemicals used, what are the possible causes, something like that. Okay. Okay, now for the cost of the hardness. Hardness, as you know, hardness mostly is mostly found in groundwater. How the hardness could actually reach the groundwater? So it comes from this phenomenon, rainfall onto the Earth's surface. part of the rain will actually seepage through the soil. This is the natural process. So the rain, once it reached the soil surface or the topsoil where there is a lot of bacteria lived near the surface. So if the rain water passing through this layer where there is the biological activity, bacteria can actually release the carbon dioxide or exhale the carbon dioxide. That is why when rainwater get attached, get interacted with the carbon dioxide, so it becomes the carbonic acids. And this one is the weak acids. Although they are weak acids, still they are powerful enough to cause the limestone cracking or the degradations, cause the damage to the limestone. According to this figure, these two are the limestone, and then interact with this carbonic acids becomes this one, calcium hydrogen carbonate. Now the equation is balanced, and these equations indicates some of the limestones get dissolved, or some kind of weathering process occur. But anyway, this is the natural process, not the coming from the human activity. Still about the theory behind, the same thing that we used to talk about, the total hardness based on the positive charge ion. The total hardness is equal to the calcium's hardness plus the magnesium's hardness. And in terms of the anion, total hardness is equal to the carbonate hardness plus non-carbonate hardness. So carbonate hardness, we all know that it is the hardness, it is the amounts of the hardness combined with the bicarbonate species. This kind of hardness we normally call the temporary hardness. This one is actually can be easily removed by just boiling the water. These types of the hardness will actually forms the scale at the bottoms of the pot. For non-carbonate hardness is the is also the hardness, but it's basically the hardness associated with some other anion, not the bicarbonate anion. And sometimes we have to measure the alkalinity, so that if the alkalinity is greater than the total hardness, we can actually assume that all the alkalinities found, all the hardness found are the carbonate hardness, no non-carbonate hardness. Okay, so these are about the background information about the hardness. Okay, now we are going to move a little bit into the process to control the hardness in water. Okay, so before we moving we move into the calculation. First, I need you to look at this example. Now it is 11:20. Okay, so we have I think we can finish this before the afternoon. Okay, so for the hardness, so just look at this table in the example 1. So this example is nothing but just try to explain about the unit conversion. For the hardness, we can actually compare them by converting the units expressed in terms of the milligrams per liter into the milligrams per liter as the calcium carbonate. You can use the molecular weight to convert, or you can use this one. According to this slide, they used the weight we normally call the equivalent weight. Equivalent weight, EW. So what is the equivalent weight? Equivalent weight is actually the weight. Another forms of the weight equivalence we use to describe the amounts of the contaminants in the solutions. But anyway, the equivalent weight is equal to the molecular weight divided by N. Then what is N? N is the number of charge exchange in case of the ion, or N may be the number of hydrogen's ion exchange in the case of the acid based reaction. But for the oxidation reductions, N is the number of the oxidation number changed. For the calciums, talking about the calciums, the charge is the +2. So in this case, N is 2. So if the calciums, so if you focus at the calciums, actually the molecular weight is 40. Then N is 2. So equivalent weight is equal to molecular weight divided by N. Okay, then you will get the equivalent weight of the calciums is 20. Molecular weight is 40, but N is 2. So that equivalent weight is 20. Magnesium's molecular weight is 24, and the charge possible charge exchange is 2 because magnesium is +2. So that N is 2. So in case of the magnesium's equivalent weight is equal to the 24 divided by 2 becomes 12. So this one is the magnesium's +2. I'm talking about the equivalent weight. And what about sodium? Sodium's is actually N it's 1. So in this case, equivalent weight is equal to molecular weight. Sodium's is 23. Equivalent weight is also 23. For this one, bicarbonate, it's just 1. So the same as the sodium, equivalent weight is equal to the molecular weight. So the value shown that in the second columns, it's expressed in terms of milligrams per liter. It doesn't say anything. If it doesn't say anything like this, it means that milligrams per liter as an ion, So 103 is the milligrams per liter of calcium 2 plus. But this one we cannot compare it with the others, whether which one is present in the greater amounts or dominant number. If you want to compare, we have to convert them into the same unit in terms of the milligrams per liter as calcium carbonate. I think I usually explain about this once when we do the labs before the midterm exams, but we did not do it in terms of the equivalent weight. We have done it in terms of the molecular weight. This one is equivalent weight. Okay, so if you want to convert the units by using equivalent weight, remember that grams divided by molecular weight is equal to a mole, and if you multiply the mole by the molecular weight again, you will get grams. Okay, this is another step. That is why in order to convert milligrams per liter as an iron to milligrams per liter as calcium carbonate, you have to multiply this one with the this ratio, equivalent weight of the calcium carbonates divided by equivalent weight of an iron. If you look into the equivalent weight of calcium carbonate molecular weight is 100. Okay, it's 100. Calcium is 40. Carbon it's actually 12, and then oxygen is actually 48. It's a 16 into 3 becomes 48. So that the molecular weight is 100. Combination of these two is 60 plus this one 40. So molecular weight is 100. But how many iron can be exchanged for the calcium carbonate? And here you will find, so it originated from the combination of calcium 2 plus and CO3 2 minus negative charge ion. So two charge can be exchanged. In this case, equivalent weight is equal to 100 divided by 2. So this one is 50. Okay, this one is 50. And what about calcium? EW of the calciums. EW of calciums. Calciums is 40. EW of calciums is equal to 40 divided by 2 because there are two charge can exchange. So equivalent weight of these calciums becomes a 20. So if you take 50 divided by 20, so 50 comes from the equivalent weight of the calcium carbonate. So all this you can also find out. For example, sulfate. Sulfate, equivalent weight of sulfate. So what is the equivalent weight of sulfate? This one is a 64 and plus 32 sulfur. So they actually becomes 96. Equivalent weight is 96 divided by 2. That is why we are getting 48 equivalent weight. So for this one is equal to equivalent weight of the calcium carbonate. Equivalent weight of calcium carbonate it's 50. Then equivalent weight of the sulfuric acid is just 48. That's why 50 divided by 48, it equal to 1.04. So if you multiply this one is supposed to be a second columns. This one's supposed to be the first column, third columns. Columns 4 is equal to second columns multiplied by the third columns. So from here and this ratio, then you get milligrams per liter as calcium carbonate here. So under these conditions, what we should do next? Then we should actually establish the bar chart. So this is how we establish the bar chart from the previous information. We separate the cation and anions. You have to put the cation above the anions, and then measure the scale. So from this bar chart of the groundwater, you can actually summarize about the what could be a total hardness. Remember that the total hardness is equal to the combinations of the carbonate hardness plus the non-carbonate hardness, excluding the sodium ion. Sodium ion is actually nothing in this case. And ions could be bicarbonate acids, sulfates and chloride. In this case, bicarbonate concentrations is less than the total hardness. So what about the remaining? The remaining it's only the non-carbonate hardness. Okay, so this chart you can use. This one is the ion concentrations divided on the x-axis, but y-axis is nothing but just try to establish the scale and put everything in the graphs. From the graphs, everything is easy to understand. And it's easy to find out what could be a total hardness, a carbonate hardness, and non-carbonate hardness. So hopefully everything is clear. There are two possible cases, as I told you. The first case is common. The carbonate hardness is less than total hardness, and the remaining is the non-carbonate hardness. But the second one is the bicarbonate HCO3 minus is actually greater than the total hardness. In this case, we can actually conclude that there will not be any the non-carbonate hardness exist. All the carbonates are the all the total hardness is the carbonate hardness. No non-carbonate hardness present. This one we measure it indirect. We make an indirect measurements for this one. We actually cannot measure the bicarbonate, but we can actually measure the alkalinity. In fact, they are not the same, but we can actually sometimes use this information to evaluate the amounts of these contaminants. Okay, so this one is about the definitions of the hardness and how we can construct the bar chart. And then again, based on these informations, can you just find out the total hardness, carbonate hardness, and the non-carbonate hardness? It is nothing but you have just to convert these into the same unit. For example, Okay, so alkalinity is equal to 200 milligrams per liter. This one is already expressed as the calcium carbonate. But then, talking about calciums is 160 milligrams per liter. It's just only milligrams per liter, not a milligrams per liter as calcium carbonate. If you want to express in terms of milligrams per liter as calcium carbonate, you have to divide it by equivalent weight of calcium and then multiply it by the equivalent weight of calcium carbonate. Equivalent weight of calcium ion. This one we have already done it previously. So it's here. For calciums, you have to multiply by 2.5. For magnesiums, you have to multiply by 4.12. So this is 2.5. So that you can find out the calcium's hardness. And then magnesiums, the concentrations of the magnesiums is 40 milligram per liter. You have to multiply by the equivalent weight of the calcium carbonate divided by equivalent weight of the magnesiums. This one is actually 50. And what about this one? This is 40, but there are two charges exchange, so that the equivalent weight of the magnesium is 50 divided by 20, because equivalent weight of magnesium is 20, but molecular weight is 40. So divide like this, you will get the, sorry, magnesium is not 40. Magnesium is 24. So this one must be a 12. That is why you get 4.12. So just multiply this by, no. 40 is correct because this is the concentrations, but equivalent weight is 12. Okay, so just multiply by this one, so you will get the in terms of milligrams per liter as calcium carbonate. Combination of these two will be the total hardness, and then the amounts of the total hardness we get, you have to compare with the amounts of the alkalinities. So I will just look at the number. So if you are doing the same process, you will get the total hardness about 567 milligrams per liter as calcium carbonate. So now you have to compare 567 and 200. So the total hardness, and this one is the alkalinity. So in this case, the total hardness is greater than the alkalinity, so that we can actually assume this one is the carbonate hardness. And then you can find out the carbonate hardness is equal to, minus the non-carbonate hardness. Then you will get plus this. Okay, again, total hardness subtracted by the carbonate hardness, then we will get the non-carbonate hardness. Okay, so in this case, non-carbonate hardness is equal to 367 milligrams per liter as calcium carbonate. Okay, so these are the answer to this example. The total hardness, this one is the total hardness. This one is the carbonate hardness. Where is the carbonate hardness? 200. 200 is the carbonate hardness. We assume all the alkalinity is equal to the carbonate hardness, and the difference between the total hardness and the alkalinity, it's the non-carbonate hardness. Okay, so these are the answer to this question. Now we will move to the chemical process that we used to remove the hardness อันนี้ยังมีคนอยู่ไหมเนี่ยนะฮะผมนี่นั่งพูดอยู่คนเดียวเดี๋ยวขอเบรกประมาณ5นาทีนะฮะแล้วเดี๋ยวกลับมาต่อไอ้เรื่องลามโซดาซอฟท์เทนนิ่งนะครับอันนี้ก็จะเป็น calculation ละนะฮะแป๊บหนึ่งไปเข้าห้องน้ำแป๊บหนึ่ง ในนี้นี่มีใครไปเป็นกลุ่มเสี่ยงบ้างเนี่ยมีไหมฮะติดเชื้อหรือกลุ่มเสี่ยงจะติดเชื้อใครเคยมีประสบการณ์บ้างที่ต้องแบบกักตัวหรืออะไรอย่างเงี้ยมีไหมokay so we just continue we still have about 10 slides left okay so now we are going to talk about the chemical reactions for the hardness removal actually there are many way to remove the hardness we can use the resins in the ion exchange process. We can use the resins like a sodium resins, and this sodium resins once we pass the hot water into the reactor containing the resin. So what will happen? This sodiums which came along with the resins will be exchanged with the calciums. So calciums in water we exchange with the sodiums in the resins, and the resins will later absorb the calciums instead, and this sodiums will get dissolved in the water. So the ion is just these two ions are just exchanged. Originally, this sodium was actually come along with the resins, but then later on it will get into the water, and calciums get inside the resins instead. So this is the exchange reactions. But now, if we want to reuse these resins, we can also regenerate these resins by putting these calciums in resins in the sodium chloride
อาจารย์ครับ
solutions
แชร์สกรีนครับ
สกรีนอีกแล้วเหรอทำไมวันนี้ผมลืมทุกครั้งเลย okay I'm talking about this slide there are many methods we can use to remove the hardness in water ion exchange could be one of the interesting method you can use the resins for example the sodium resins and then if we apply the hot water into the containers containing the resins, the exchange between the calciums and sodiums can actually take place. Calciums will be associated with the resins, and then sodiums will get into the water. And at the end, these resins, we can also reuse it. We can actually put this resin associated with calciums into the sodium chloride solutions. The sodium chloride solutions concentrated one. The concentrated sodium chloride solutions will leach all the calciums, and then the sodiums in the solutions will get into the resins again. That is why we can reuse this one. So this one can be used to replace the calcium ion in water again. But the problem with this ion exchange softening is, see here, we exchange sodiums with the, we exchange calciums with the sodiums. So at the end, the amounts of sodiums in water will increase. So we now we can remove calciums, but we get sodiums. So I don't know which one it could be better. Sodiums also increase the blood pressure actually, and it also increases the total dissolved solids in water. If the concentrations is not too high, it doesn't matter. But if the concentrations is high, it may also not good for the human health in terms of the drinking water. But for other purposes, it may be okay. In industry, they also don't want calcium, so but they don't have the problem with the sodium, and that is fine. So this could be one of the methods we use to remove the we used to remove the sodiums, calcium and magnesiums of the hardness from water. This is how it works. And now we come back to the conventional method. The conventional method that we use to remove the hardness is the lime soda softening. Lime soda softening is a kind of series of chemical reactions. How we can remove calcium and magnesiums. So first you have to be clear. We have various types of the hardness based on the cation. Total hardness is equal to calcium hardness plus the magnesium hardness. And in terms of the anion, the total hardness is equal to carbonate hardness plus non-carbonate hardness. Okay, so we want to make them เดี๋ยวแป๊บหนึ่งนะ I have got the core ฮัลโหลสวัสดีครับเอาไว้ที่โต๊ะรปภได้ไหมครับครับแล้วเดี๋ยวเที่ยงเดี๋ยวผมไปเอาเนาะเดี๋ยวก่อนบ่ายครับครับครับอันนี้จากของอะไรฮะ Curly หรือว่าของ DHL โดยตรงเลยครับครับครับเดี๋ยวมันจะมีโต๊ะรปภข้างล่างนะครับเดี๋ยวลงไปเดี๋ยวไปเอาครับครับครับครับครับครับครับโอเคครับขอบคุณครับokay okay so we have several types of the hardness in terms of the positive charge hardness. We classify into two types, calcium hardness and magnesium hardness. In terms of the negative charge or carbonate species and non-carbonate species, like this. Okay, for this one, for the lime soda softening, normally we try to remove this one. This could be our first priority to remove. Remember that the hardness is not the parameters we try to remove 100%. So if it contains, if the groundwater, for example, contains the hardness 400 milligrams per liter as calcium carbonate, we will reduce the hardness. We try to remove the hardness and reduce the hardness in water to be in the range of 75 to 120 milligram per liter as calcium carbonate only. That means we have to remove around 300 milligrams per liter in this case. So we try to remove around 300 milligrams per liter in this case. And we need to remove the calcium hardness first, and then for example, if we want to bring the 400 to around 100, we have to remove 300. So if the 300 is the carbonate hardness, then we don't have to go for the magnesium hardness removal. So if the all 300s are the calcium hardness, if all these 300 milligrams per liter as calcium carbonates to be removed, is the calcium hardness. We don't have to remove the magnesium hardness. Okay. And in terms of the negative charge, our first priority is we also try to remove carbonate hardness first. So if it's not enough, then we go for the non-carbonate hardness. For example, if we have to remove like 300 milligrams per liter as calcium carbonate, and then this 200 milligrams per liter is the carbonate hardness, and then another 100 milligrams per liter, it's a non-carbonate hardness. So we try to remove this one. If there is a non-carbonate hardness to be removed, then we go for the non-carbonate hardness remover. So we would rank like we try to first remove the calcium hardness, and then we will also remove the carbonate hardness first in terms of the negative charge. And if it's enough, if it meet the requirement, we will not go for the magnesium hardness or the non-carbonate hardness. Why? The reaction will tell you these reasons, because we are not going to remove 100%. For the calcium removal and magnesium's removal, for calcium's removal, if the calcium presents in water, and if we want to remove, we'll precipitate these calciums with the carbonate species. So if we use this one, and if we add this one into the water, we can precipitate these calciums in terms of the calcium carbonates. This is the precipitated forms identified by the solid state. For magnesiums, we cannot do the same as the calciums, although they belong to the groups, second groups in the periodic table, but they have different chemical characteristics. Magnesiums never precipitated with the carbonate. So if you want to remove the magnesiums, you have to precipitate these magnesiums with the hydroxide ion instead. So magnesium hydroxide is the precipitated forms of the magnesiums. So this is the basic idea of how we can remove calciums or magnesiums. So this these reactions are possible only when the pH is above 10.3 for the calciums, and it must be above the 11 for magnesiums. So it means that we have to adjust the pH. So we have to bring the pH of the water to be above 10. Only above 10 we can actually remove the hardness. Why? If you look at the reaction, okay, if you look at the reactions, okay, so before we move to the reactions, what we have to do for the softening, for softening, first we need to increase the concentrations of the carbonate, because we need carbonate to precipitate calciums, and we also need the hydroxides to precipitate magnesiums. Okay, so we need to increase these two iron, the concentrations of these two iron by adding the chemicals, and then we convert bicarbonate to carbonate by adding the hydroxides, because these hydroxides will raise the pH to be above 10. So at the pH above 10, this one will be converted to the CO3 minus 2. Anyway, we need this one, hydroxide ion. The source of the hydroxide ion is the lime. That is why we use lime to soften the water. The lime is calcium hydroxide, CaOH2. This one is the lime. But if we use the CaO, This one is called a quicklime. They are different, but the most commonly used is this one, calcium hydroxide or a lime. This one may be required. Extra amounts of the carbonate ion may be required. So if it's required, we may need to add sodium carbonate. Sodium carbonate, the common name is the soda ash. This one, the common name is lime. And this one, the common name is the quicklime. Okay. So sometimes we have to supply the carbonates by adding the sodium carbonate or the soda ash. Okay, for the reactions, this one is the about the why we have to add these chemicals. But if you look at the reactions, you will find at first we need to neutralize the water in case if there is the acids if there is the acidity due to the dissolve of the carbon dioxide gases. So we have to add this one. The limes will neutralize carbon dioxide or the carbonic acids, and once it reacts with the carbon dioxide in water, it becomes the calcium carbonate. This is the precipitate forms. This one is nothing about the hardness removal, but just adjusting the pH to be above 11 and also the neutralize the acidities in water due to the dissolve of the carbon dioxide. And the next is this calcium ion in water. Additions of limes for the precipitations of the calciums in water. So this one and under the presence of the bicarbonate ion, combination of these two is called the carbonate hardness. Under the presence of this one, calciums, and then additions of limes, these reactions will take place. What is the end products of these reactions if there are three chemical agents interact with each other? Calciums, iron, under the presence of limes, it will react with the carbonates, and this one will be formed. Precipitate forms of the calciums will be the products of these reactions along with water molecules. Here we can say that 1 mole of calciums required 1 mole of limes to precipitate to remove the calciums. Okay, to precipitate it as the calcium carbonates. 1 mole of calciums required 1 mole of limes. This one is already there. And now if we need to remove the magnesiums, this one is the magnesiums. In order to precipitate the magnesium must be precipitated in forms of the magnesium hydroxide, not the magnesium carbonate. Magnesium carbonate is still a aqueous status. This is not the precipitated forms. So additions of limes will have to promote these reactions. Limes under the presence of the carbonate hardness or the bicarbonate ion, these reactions will take place. Here we will get the magnesium carbonates along with the precipitated forms of the calcium carbonates, but still magnesium is there. Then we have to add another mole of limes to precipitate these magnesiums. So additions of one extra amounts of the limes added will react with the magnesiums due to the magnesium carbonates and create the magnesium hydroxide. So this one is the precipitated forms of the magnesiums. And this one is again generated. So we can say that in order to remove the magnesiums, one mole of magnesiums required 2 moles of LAMS. That is why in the previous slides, it comes to the conclusion that we remove the magnesiums later because the removal of the magnesiums is more expensive than the removal of the calciums. Why? According to the reaction, you can see the removal of the calciums required only 1 mole of LAMS, but for magnesium, 1 mole of magnesium require 2 moles of LAMS, so a double amount of LAMS requirement. So these are about the calcium and magnesium hardness, and also the carbonate hardness remover. Now, if you look at the non-carbonate hardness, if we need to remove non-carbonate hardness means the calcium associated with other anion, not the bicarbonate. Sulfates, for example, chloride, for example. So for this one, calciums, just the calcium presence. So in order to remove the calciums due to the calcium's non-carbonate hardness, you need to use sodium carbonates or the soda ash. So this one, 1 mole of the soda ash required for the removal of 1 mole of the calciums. At the end, we get the precipitated forms of the calcium carbonates, and 2 moles of sodiums get into the water. And for the magnesium is always the problems. 1 mole of magnesium non-carbonate hardness due to the magnesiums. 1 mole of magnesium requires 1 mole of LAMS to precipitate the magnesiums, and then just like the ion exchange, so magnesiums get interact with the hydroxides, become the magnesium hydroxides. But additions of LAMS is not enough because if we do it like this, calcium just get into the water, and this is still the hardness. We want to completely remove calcium and magnesiums. So for these calciums, we need another moles of the soda ash so that we get the precipitated forms of calcium carbonate. So for non-carbonate hardness, anyway, we need the soda ash. Soda ash is much more expensive than the LAM. That is why, as I told you from the previous slide, for hardness, we try to reduce the amounts of hardness. If it's beyond the appropriate range, we bring them into the optimum rank. So we need to remove some certain amount of hardness. We don't have to completely remove them. It's not necessary. So if we have to remove some of the hardness, we will select the calciums. We will select the carbonate hardness as our first priority is to take them out from the water. If it's still if there are some hardness left and we have to remove them, we will go for the magnesium hardness, and we will go for the non-carbonate hardness removal. Anyway, it looks complicated, but if you come back to these diagrams, it will be easy. So according to this reaction, we have to add LAMS. Okay, so this is the amount of LAMS required. Okay, so before we talk about the amounts of LAMs required, these are the summaries of the process limitation. So several reactions we can remove the hardness, but in reality, we cannot remove them 100%. For example, even though we add the LAMs and soda as per the ratio in the stoichiometric equation, but still at the end, there are some certain amounts of the calcium hardness left. We cannot bring them to zero. Anyway, for the calcium hardness, there's some certain amounts left in water, approximately 30 milligrams per liter as calcium carbonate will be anywhere present in water. Even we add a lot of LAMs into the water, similar to the magnesium's hardness anywhere, it will be there for 10 milligrams per liter. So in combinations for the hardness, anyway, calcium and magnesium's hardness still present in water 40 milligrams per liter. Even we add a lot of LAMs, even we add extra amounts of the LAMs beyond the stoichiometric requirement, still we cannot get rid of 100% of the hardness. Still, it's there, 40 milligrams per liter. Cannot produce free of hardness. And reasonable removal excess amounts of LAMs beyond the stoichiometric is provided. Minimum excess of 20 milligrams per liter of calcium carbonate it's common to be added to drive the reactions slightly greater than the stoichiometric requirement. Magnesiums are in excess of 40 milligrams per liter of as calcium carbonates normally form the scale, so we prefer to leave the magnesiums less than 40 milligrams per liter. This could be one of the considerations why we do the softening. Less than 20 milligrams per liter as calcium carbonates. I'm talking about the LAMs addition. So this could be a basic excess. Sometimes we have to add more LAMs for the equal to the amounts of the magnesiums to be removed. Sometimes we have to add LAMs in excess if the magnesiums is greater than 40 milligrams per liter. So we have to add extra amounts of LAMs 40 milligrams per liter. But add LAMs greater than 40 milligrams per liter, it's not very useful. It will not help to drive the reaction. It is meaningless. We cannot, if you add it larger than a 40 milligrams per liter as a calcium carbonate. So these are about the extra amounts of LAMs additions under the presence of the magnesiums. So finally, in conclusion, how many kilograms or how much LAM required for the softening the hard water. So first we have to determine the amounts of the carbon dioxide, and then we add LAMs equal to the amounts of the carbon dioxide present. Then second, we add the amounts of the bicarbonates. We add the LAMs equal to the amounts of the bicarbonates. Third, we add the LAMs equal to the amounts of the magnesiums to be removed. And here are the reasons why we have to add LAMs. We add LAM equal to the amounts of required excess. Magnesium's These are for the carbonate hardness remover. And the last one, if we still have to remove the non-carbonate hardness, we will add the soda equal to the amount of non-carbonate hardness removal. So these are the reasons. But anyway, as I told you, all these chemical reactions and the amounts of lamps required looks actually complicated, but it's easy when you look it back at this diagram. So according to this diagram, it is quite simple. So you can just follow these diagrams. At first, we have to add lamps equal to the amounts of the carbon dioxide. And then we have to add lamps equal to the amounts of the bicarbonate. And then come to the next box. You just check the amounts of the magnesium. So if it's greater than 40 milligrams per liter, we will add lamps equal to the amounts of magnesium minus 40. Just go it one by one. And then we add extra amounts of lamps to drive the reactions. It depends on the amounts of the magnesium present. Or here, all the units expressed in this figures are as calcium carbonates. Okay, all the units milligrams per liter, though they did not write like a milligram per liter as calcium carbonates, but you should be recognize that this milligram per liter, it's actually milligram per liter as calcium carbonates. They haven't written here, but we must know it. This one is milligram per liter as calcium carbonate. So at the end, we just check whether there is the non-carbonate hardness to be removed. So if we have to remove the non-carbonate hardness, we will add the amounts of the soda equal to the amounts of non-carbonate hardness to be removed. Okay, so these are all about the hardness, and I think in terms of the cost content in this chapter, we have already finished. Okay, so now just come to the example. By 12:30, you will receive the assignments. So the assignments which will be distributed at 12:30 cover the sedimentations, filtrations until the finish of these chapters, including this one. But in this presentation, there is no example. Okay, I will take the question in the assignments to show you how we can solve this, how we can find out the amounts of lamp and sodas required. Okay, the question number 12. These are the wastewater water characteristics. Sorry, water compositions expressed in terms of the okay, so it's already in terms of the milligrams per liter as calcium carbonate. Suppose it's already in terms of the milligram per liter as calcium carbonate. I'm not sure whether this is a mistake or it is like this. Milligram per liter as ions or milligram per liter as the calcium carbonates. But
อาจารย์ครับ
anyway ครับ
first part exam นี่เราสอบจนถึงเรื่องนี้หรือเปล่าครับ
เรื่องนี้ฮะ
โอเคครับ
บทนี้ทั้งบทเลยนะฮะ บทนี้ทั้งบทเลย okay, for this one, water composition, this water consists of calcium, this milligrams per liter as calcium carbonate, carbon dioxide 29.3 milligram per liter as calcium carbonate. If it's a milligram per liter as an iron, you have to first convert everything into the milligram per liter as calcium carbonate by using this ratio. For the carbon dioxide, carbon dioxide molecular weight is 44. But in fact, concerning as far as the dissolve of carbon dioxide in water is concerned, so carbon dioxide in combinations with water will produce H2CO3. This is a carbonic acid. This carbonic acid can actually propose two protons, so that if we want to determine the equivalent weight of the carbon dioxide, this will be always equal to molecular weight divided by 2. 2 protons are exchanged. So equivalent weight is 44 divided by 2. This is the EWs of the carbon dioxide, and then the EWs of the this one is 50. So the ratios of the carbon dioxide, if you want to convert it into the milligrams per liter as calcium carbonate, you can take this ratio, which is equal to 2.28. So this is the ratios for the carbon dioxide. In case if you have to convert it from the milligram per liter as iron to the milligrams per liter as calcium carbonate. Okay. First, what you really need to do. Okay. This one is milligram already expressed in terms of milligrams per liter as calcium carbonate. So what you really need to do in the first step, you have to start with the sketching the bar chart. You have to start sketching the bar chart. And this is the positive ion, so the cation. And then carbon dioxide is not an ion. So we put it here. This one is a CO2, as it is already in milligram per liter as calcium carbonate. So it's all the same units. This one is 29.3. Then for the calcium, so it's 149.2. Magnesium is another 65. So how much is it? 49.2 plus 65.8 ได้เท่าไหร่ใครมีเครื่องคิดเลข65.8, it becomes 215. And the last one is 17.84. So this will be 32.4. And then here is the carbonate bicarbonate ion. So this is 185 sulfate. (185) plus so this one is sulfate, and this is 14.8. And this will be again, exactly the same, 232.4. This one is a chloride. So here, if I ask you what will be the total hardness and what will be the values of a carbonate hardness, the total hardness is, of course, it is 15 milligram per liter as calcium carbonate. And in this case, bicarbonate is just only 185, but total hardness is 215. So the carbonate hardness in this case would be equal to the amounts of the alkalinity, 185 milligrams per liter as calcium carbonate. And then non-carbonate hardness is equal to the difference between total hardness and the non-carbonate hardness. This is 30 milligrams per liter as calcium carbonate. Okay, so these are the types of the hardness found in this water. Now we are going to determine the amounts of lambs and the amounts of soda if we want to if we want this water to have the hardness remains only 90 milligrams per liter. Remember that we have the total hardness as much as 215, so we have to bring them to be not exceeding 90 milligram per liter as calcium carbonate. So that the question is what will be the amounts of lamb required. So we have to go according to the diagram. You can make use of this diagram. First, we add lamb. First, we add lamb equal to the amounts of carbon dioxide. So what will be the amounts of carbon dioxide? This one is the amounts of the carbon dioxide, 29.3. This one is the amounts of lambs we add to neutralize the carbon dioxide. And then the second steps, we add lambs equal to the amounts of the bicarbonate ion. You have to go according to these diagrams. This one. Okay, if we need to add the amounts of lambs equal to the amounts of bicarbonate ion, it means that we have to add lambs equal to 185 the units or milligram per liter as a calcium carbonate. The next one is the magnesium concentrations. The magnesium concentrations. Magnesium is greater than 40. We have right now we have the magnesium as much as 65. So yes, it is greater than 40 because we have 65. We have to add lambs equal to magnesium minus 40. Then we have to add lambs equal to magnesium minus 40. So we have magnesium 65.8. So we have to add lambs equal to 25.8. Okay, 65.8 minus 40. Then the next now is the excess lambs. Is the magnesium minus 40 greater than 40? No, because we have only 25. Less than 20? No, right? It is in between 20 to 40. So if it's in between 20 to 40, less than 40. No, okay, so we have to come to this block. No, we have to add lambs, extra amounts of lambs. We have to add the extra amounts of lambs equal to the magnesium minus 40. Again, we have to add the magnesium. We have to add lambs equal to the amounts of magnesium minus 40. So this one is lambs excess. This one is excess. So we have to add the same magnesium minus 40, 25.8, the same as this one. So how much carbonate hardness? How much lambs required in this case? How you have to combine all these four. So the total lamb required, it's equal to the combinations of these four. I don't know how much would that be. 185 plus 29.3. So this will be 265.9 milligram per liter as a calcium carbonate. So this is the amount of lambs required. Once you remove the calcium hardness, once you add the lambs, calcium hardness is expected to be removed, but they are not 100% removed. Okay, even you add it according to the procedure, there will be about 40 milligrams of carbonate hardness remain. This is the limitation. This is the limitations of the this process. As I told you here, anyway, even we add extra amounts of lambs, we add the excess lambs, but still 40 milligram per liter as calcium carbonates remain. Okay, it means that if we add it like this, we still have 40 milligrams per liter, and now left. Okay, we still have 40 milligrams per liter left. It doesn't mean that if we add it like this, 185% will be completely removed. No, only 145 is expected to be removed, but 40 milligrams per liter of lime still remain, plus a non-carbonate hardness. So total hardness left in this water, it's equal to 30 plus 40, equal to 70 milligram per liter as calcium carbonates. Now, without doing anything with the non-carbonate hardness, only additions of lambs, we can remove some certain amounts of the carbonate hardness. So with the non-carbonate hardness remain, we can say that you can expect it to have the hardness in water approximately 70 milligram per liter. And if you compare with the requirements is 90. So now we have 70. It comes to the last conclusion. Last question. Do we really need soda? for the non-carbonate hardness remover. As this one is already less than 90, so there is no need to remove the non-carbonate hardness. Okay, there is no need to remove non-carbonate hardness. But if the non-carbonate hardness is far like 80 milligrams per liter instead, if it's 80, okay, if it's 80, what does it mean? If it's 80 combined with 40, so it will be 120. It's over 90. It's over 90. So how many milligrams per liter of the non-carbonate hardness and we need to remove? So we need to remove 30 milligrams per liter, right? Another 30 milligrams per liter of NCH need to be removed because it's over the requirement. So if we have to remove 30 milligrams per liter as calcium carbonate of non-carbonate hardness, so how much do we have to add? How many milligrams per liter of soda do we need to add? So in the final steps, if it exceeds the requirement, it comes to the last box. If there is the non-carbonate hardness to be removed, we have to add the soda equal to the amount of non-carbonate hardness to be removed. So according to the examples I explained, in case of we have the non-carbonate hardness as much as 80 milligrams per liter, in combination with this one, it means that we have combining these two becomes 120, and the hardness we want only 90. So it means that around 30 milligrams of the milligrams per liter as calcium carbonate of non-carbonate hardness we have to remove, and then we have to add the soda equal to 30 in this case. So we have to add soda ash or sodium bicarbonate 30 milligrams per liter as calcium carbonate. So finally, so what you have to add? You have to add soda equal to this amount, lambs. But in this question, as the non-carbonate hardness in combination with what is left 40 milligrams per liter, still under the requirement, it is okay. But if it exceeds the requirements, like in this case, you have to add the soda. But answering to this question, of course, you need this one. You may not need the soda. But just in case if it exceeds the requirements, you have to add it. Okay, just go one by one, a block by a block like this. Okay. That is all about the chapter 6. So now we have already completed the chapter 6. Do you have any questions? The next 2 weeks, we still have 2 chapters left. We will talk about the wastewater treatments and also the sludge treatments processes. มีคำถามอะไรไหมฮะเกินเวลาไปหน่อย
การบ้านอาจารย์จะเฉลยไหมครับ
มันจะมีสัปดาห์หน้าที่เราไม่ได้เรียน lab ใช่ไหมแล้วเราก็จะมี discussion นะเดี๋ยวถ้ามีเวลาเดี๋ยวเราเอาการบ้านเหล่านั้นมาพูดกันอีกทีหนึ่งช่วงเวลา lab
ครั้งสุดท้ายเลยครับอาจารย์
lab ครั้งไหนอะสัปดาห์หน้ามั้งน่าจะสัปดาห์หน้า
ไม่หมายถึงว่าสัปดาห์นี้เป็น lab ครั้งสุดท้าย
lab ครั้งสุดท้ายก็สัปดาห์หน้าทีแรกคิดว่าจะมี experiment ไงแต่ว่าเราเข้ามาทำ experiment ไม่ได้ไง
ครับก็เลยอาจารย์อาจจะเฉลยเป็นของอาทิตย์หน้าเนาะ
เป็นอาทิตย์หน้าตอนบ่ายก็เดี๋ยวเราเอา assignment ต่างๆมาคุยกันแล้วก็discussion ของlab report ด้วยนะฮะ
ครับ
อาทิตย์นี้ผมจะบอกว่า lab เดี๋ยวผมจะเลิกเร็วไม่ discuss นะฮะเพราะว่าเดี๋ยวผมต้องไปมีภารกิจในเมืองตอนบ่าย 3ต้องออกแต่ว่าบ่าย 3:30ยังเจอกันตามเดิมนะครับโอเคมีอะไร